Hello, everyone. My name is Dr. Mihir Ghosh. I'm the Assistant Professor of the Department of Chemistry, SRM Institute of Science and Technology. Good afternoon, everyone. So, today we'll discuss the study of electrochemistry. Electrochemistry is an important branch of chemistry because it connects chemical reactions with electricity, batteries, corrosion, electroplating, fuel cells, sensors, and many analytical methods are based on electrochemistry. In this lecture, we'll understand the redox reactions, electrolytes, galvanic cells, electrode potentials, and Nernst equations, concentration cells, potentiometer titrations, Latimer diagram, and solubility product. So, by the end of this class, you should be able to define solubility product, explain the galvanic cell, its representations, define electrode potential, standard electrode potential, write and apply the Nernst equation, and solve simple electrochemical numerical problems. This is the most important ideas are electron transfer, electrode potential, and spontaneity. So first, let's discuss about the electron transfer reaction. Electron transfer reactions are called oxidation reduction or redox reactions. In these reactions, one species loses electron and another species gains the electron. Electrochemistry studies the interconversion of electric chemical energy and electrical energy in a battery. A spontaneous chemical reaction produces electricity. In electrolysis, electricity is supplied to force a non-spontaneous chemical reaction. Therefore, a battery converts a chemical energy into a chemical electrical energy, whereas electrolysis converts electrical energy into chemical energy. So, some terminology of the redox reaction before we proceed. Oxidation means the loss of electron. All of you know that one. It also means the increase in oxidation number. Reduction means the gain of electrons and decrease in oxidation number. And an oxidizing agent accepts electron and gets reduced. A reducing agent donates electrons and gets oxidized. In simple rule, there is LEO, LEO. Loss of electron is oxidation. Another useful rule is oil rig. Oxidation is loss, reduction is gain. Okay. I hope this way you can remember very easily. When a copper is dipped into a silver nitrate solution, we can see here the copper metal loses electrons and enters the solution as copper ions. At the same time, silver ions gains electrons and deposit as metallic silver. So the reaction is copper plus 2Ag positive gives the plus gives the copper to positive to silver ions. Okay, the solution becomes a blue because copper to positive ions are formed. This is redox displacement reaction. Here, copper is oxidized, silver is reduced, and copper acts as a reducing agent, and the silver ion acts as a oxidizing agent. When magnesium, zinc, or aluminum is dipped into copper solution, these more reactive metal displaces copper from the solution. For example, zinc, uh, zinc plus copper sulfate solution gives the zinc sulfate and copper. Okay. And on the right side, we can see the reddish brown copper deposit appears on the zinc surface, and the blue color of the copper sulfate gradually decreases. Okay. Now, what is the electrolytes? So, an electrolyte is a substance that conducts electricity in molten state or aqueous solution because it produces freely moving ions. For example, sodium chloride is in solution from does not conduct electricity, but ions are fixed in the crystal lattice. But molten sodium chloride or sodium chloride dissolved in water conducts the electricity, which because sodium and chloride can ions can give the ions freely. Now about the electrolytes. Strong electrolytes, weak electrolytes. So what is the strong electrolytes? Strong electrolytes dissociates almost completely into ions in the solution. Therefore, they conduct electricity efficiently. Let's say for the hydrochloric acid, sodium chloride. These are all strong bases. So hydrochloric acid is strong acid, and sodium chloride is a strong sodium chloride or strong base. And most soluble salts, hydrophobic acid produces hydronium and chloride ions, while sodium chloride produces sodium and chloride ions. Now about the weak electrolytes. Weak electrolytes dissociates only partially in the water. Therefore, the solution contains both molecules and ions. Acetic acid and ammonia are common examples since fewer ions are available in the carrying for carrying the charge. Weak electrolytes conduct electricity poorly compared to the weak electrolytes. Electrochemical cell. Electrochemical cells are devices in which chemical energy and electrical energy are interconverted. These are two major types in an electrolytic cell. Electrical energy is used to cause a chemical change in a galvanic or voltaic cell. A spontaneous chemical reaction produces electrical energy. So galvanic cell include like chemical cells and the concentration cell. Now, what the oxidation and reduction potential? When oxidation occurs at an electrode, we may write an oxidation potential. When reduction occurs at an electrode, we write as a reduction potential. Um, Now, what the standard electrode potential? Standard electrode potential, when written as a E0, is the potential of an electrode under standard conditions. The usual standard condition are one molar concentration of ions in 1 atmosphere pressure for gases at 298 Kelvin or 25 degrees centigrade. Salt bridge. Why we need the salt bridge? So salt bridge is generally a U-shaped tube containing a concentration solution of an inert electrolytes, often the potassium chloride, potassium nitrate, or ammonium nitrate in agar-agar gel. The salt bridge has three major most functions. First, it completes the electrical circuit in a cell. Secondly, it maintains the electrical neutrality in both half cells without participating in these reactions. Third, it prevents direct mixing of the two solution and minimizes liquid junction potential. In the Daniell shell, zinc ions accumulates in the zinc hub cell. Therefore, anions from the salt bridge moves towards the zinc side. In the copper hub cell, copper ions are moved, so cations move toward the copper side. So here we are showing exactly how it works. So first, this is the construction of the linear cell. First, what exactly happens? So zinc electrode is dipped in the zinc sulfate solution, and copper electrode in the copper sulfate solution. Okay. So first, in the zinc sulfate solution, zinc start to leach in the solution. Okay. And when zinc sulfate start to leach in the zinc sulfate solution, this is the zinc sulfate solution. So extra two electrons will accumulated here. So extra all the electrons will move from this direction to this direction. So the when the electron move here, so electron reached here, and finally this electron captures the sulfur copper 2 plus, interacts with the electron, and finally deposited the copper. Okay. So eventually we can see the zinc will become thinner and copper electron become thicker. So, so gradually it happens, one, two, three, four, like this. So we are showing here exactly how the zinc leaches and copper start to deposit. Okay, but once after the reaction started, after a few minutes, that we can see the so many due to the presence of so many concentration of zinc 2 plus solution. Due to the high concentration, zinc 2 plus cannot leach in the solution. So same way, like when the in there we have the copper sulfate solution, they as the all the copper is deposited as copper sulfate solution, copper 2 plus deposited as copper. No other copper 2 plus ions are available to deposit over the copper electrode. So to make this neutrality, so that means in this situation the whole electrode stopped. So no electricity actually generates. Now to restart this cell, we need a salt bridge, which will make the electrical neutrality, and finally it will start the reaction again. So all the half cell reaction is showing here. How zinc is start to leach and giving the electron, and how copper 2 plus takes the electron and deposits as copper, and the final this is called the net reaction. So net reaction, this is the half cell reactions. I hope it is very clear for all of you. Okay, now the electrochemical cell. So electrochemical series. The electrochemical series arranges the electrodes according to their standard reduction potentials. A species with more positive reduction potential is more easily reduced and act as a stronger oxidizing agent. A species with more negative reduction potential is more easily oxidized and act as a stronger reducing agent. So the series we are showing here, it helps to predict the displacement of the reaction, spontaneity, and products during the electrolysis. Okay, so now about the standard electrode potential or standard hydrogen electrode. To compare all electrode potential, we need a reference electrode and the standard hydrogen electrode or SHE is assigned as a standard potential or 0 volt. The half cell reaction is two hydrogen atom ions plus two hydrogen gives hydrogen gas. Under standard condition, hydrogen gas is at 1 atmosphere pressure. Hydrogen ion concentration is 1 molar and temperature is 900 Kelvin. And we are giving some numericals here. Let's say there is a standard reduction potential zinc 2 plus zinc and copper 2 plus copper having the reduction potential values minus 0.76 volt and plus 0.344 respectively. Now calculate the potential of the cell. To calculate the the potential of the cell, we have to first we'll go to their half cell reaction. In the half cell reaction, you can see zinc is leaching as a zinc to Zn2 plus and copper is reduced by copper having the 2 electron. Now for the zinc 2 plus 2 zinc, so that means it is given as a reduction potential value. So we have to convert it in the oxidation potential value. So that's how we have changed the sign here as a oxidation potential value from minus sign to plus sign and copper 2 plus 2 copper. So it is a reduction potential value. So we can see in this reaction, it is a reduction process happening. So without changing their sign, we directly will use this value without changing their sign. So simply we'll get like 1.1 volt. In order to force the reaction to take place in the reverse direction, a potential more than 1.1 volt should be applied externally, hence the denudation is zero. So that means to make this cell active, we need a energy 1.1 volt, more than 1.1 volt. Then only this reaction can happen. Now with the another numericals, calculate the standard EMF of a cell that uses the magnesium 2 plus, copper 2 plus, half cell reaction at 25 degrees centigrade. So first we see here both of these are oxidation potential values are given copper 2 plus. So that means both cases oxidation is happening. So in the half cell reaction we can see in magnesium to magnesium, that means we need a reduction potential value. It is given here and copper 2 plus 2 copper. So it is a reduction potential value again. Now for the overall reaction, we can see the reaction is like this. And we see magnesium to magnesium 2 plus conversion. That means oxidation process. That means we have to change the sign here. So that's why we change the sign here, minus to plus. And for this one, for copper 2 plus 2 copper, we see it's like a plus sign. So it's a reduction process. So we can take it like as it is from without changing sign. So simply the reduction standard potential value is 2.71 volt. Okay. Now about the concentration cell. In this concentration cell, we don't need any specific kinds of electricity here. So specifically, the electrodes are same, but the change, the electrolytes having different concentration. So here we can see due to the different concentration, the cell start to work like how this way, how it is working. So copper start to leach because this is less concentration solution, and the extra two electron will just move to this way to this direction. And when this copper extra two electron will reach here, due to the ability of the copper 2 plus, this is a more copper concentrated solution, the extra copper 2 plus the copper 2 plus ion start to take the electron and will deposit it over here. So that's how you can see here it will start to leach and this will deposit here. So here the driving force is only the concentration of the electrolyte solution. We no need any specific kinds of electricity to run this cell. This is the beauty of this concentration cell. I hope you enjoyed this video. So in the next video, we'll discuss about the EMF of the cell and free energy change of the reactions. So how exactly it happens, we'll discuss in our next video. Thank you for your patience. See you in the next video. Thank you.